Now we will see that sometimes we can directly determine the elastic curve by knowing just the distributed load. So here we can see that, for example, for beam AB, you have that AB is subjected to a uniform distributed load that is rectangular. And then going back to the definition of relation between bending moment and shear and distributed load, we can say that the first derivative of m with respect to x is the shear. And we know that the derivative of shear is minus wx, taking wx positive downward. So if we replace v by, if you want, dm by dx, then we can say that minus wx is the first derivative of v and the second derivative of bending moment with respect to x. And now we have already established that the second derivative of m with respect to x is equal to ei times the fourth derivative of y with respect to x, because we have seen before that the bending moment m can be written as ei times the second derivative of y with respect to x. So now if we apply the fourth derivative, if we apply the second derivative of m with respect to x, this means that we should derive the bending moment 2 times with respect to x. And therefore, second derivative of m will be ei times fourth derivative of y with respect to x. And this will give us the following differential equation that will relate directly the fourth derivative of y with respect to x, where y represents the deflection, to the distributed load wx. And then, if you want to find y, no need to, if we just have a distributed load of known function, okay, all we have to do, instead of going to search for the bending moment, we can directly starting the integration from wx, but we have to integrate 4 times. So to reach y, we have to integrate 4 times, and therefore EIYX is minus the fourth integral of wx dx plus 1 over 61x cubed plus 1 over 2 c2x squared plus c3x3 plus c4. Why we have this form? Because let us do the derivation step by step. So if we consider first the following formulas, the first step is to integrate the first time with respect to x. The first integration will give us that ei times the third derivative of y with respect to x is equal to minus integral of omega x dx. And of course, we don't forget to add the constant, so plus c1. Now, when we integrate the second time, we get ei times second derivative of y with respect to x squared equals to, now we have double integration of, so when you integrate the integral, you get minus double integral of wx. And when you integrate c1, you will get plus c1x, and you have plus c2. Now, you integrate again. When you integrate again, you have ei times dy by dx equals to minus. So now you have the third integration. So minus integral dx, integral dx, integral wx dx plus c1 x squared over 2 plus c2x and plus C3. And finally, the force integration. The force integration will give you the result shown here. That the minus force integral of Wx plus C1 x cube over 6 plus half C2 x squared plus C3x plus C4. So this is the final form of EI times y of x. And here we have 4 constants of integration, C1, C2, C3, C4. To find this constant, we need to apply 4 boundary conditions. And the 4 boundary conditions that we can apply here, for example, are the following. If you look at A and B, first at A, you know that the deflection is 0 and the slope of deflection is 0. So you have already 2 conditions, one on y, one on dy by dx, which is the slope. And we said that we approximate the slope by angle theta, because theta is relatively small. And then you need still 2 other conditions. Now the type of conditions that we'll use now is a little bit different, because we don't have information on y and slope of y at any point other than A. So we just know that at A, y is 0 and dy by dx is 0. But what we have information about is the shear and bending moment at B. Why? Because this is a free end. You know that at a free end, shear is 0 and bending moment is 0. So here you don't have any concentrated force, you don't have any concentrated couple. So, and for the distributed load, it will not give any value of V and M, because if you just do the cut here, don't have a distance, so to have V and M. Therefore, whenever you have a free end, this means that at this point you don't have a concentrated force or you don't have a concentrated moment, then you can say that at this point you have 0 shear and 0 bending moment. And you know that shear is dm by dx. Okay, so if you want in this stage, when you do dm by dx, dm by dx is EI times the third derivative of y with respect to x. So you can, when you know a bending moment, you can apply the condition on the third derivative. So here, you have that V is dm by dx. So whenever you have dm by dx, you can apply the boundary condition on V, okay? Because Vx is equal to dm by dx, which is proportional to the third derivative of y with respect to x. So knowing the value of V at point B will allow you to write a boundary condition applied on the equation of the third derivative of y with respect to x to get an equation, a third equation that will allow you to solve for your constant. Now, a fourth equation, okay, will be to consider that the bending moment M, so the bending moment M is equal to 0. And we know that the bending moment M is equal to EI times the second derivative of y with respect to x. So now you can say that if I know at B what is the bending moment, I can apply the boundary condition for the equation of the second derivative of y with respect to x in order to get a fourth equation. And then I have 4 equations, 4 unknowns, which will allow me to find my constant C1, C2, C3, and C4. Now, we already introduced the concept of statically indeterminate beams. And we said that the analysis of deflection will help us into finding undeterminate reactions by statics. So, for example, here in this figure, you can see a beam that is supported by a fixity at A and a roller at B. So we have in total 4 reactions unknown: AY, AX, MA, and BY. And statically, we can just write 3 equations. If you write 4 equations, you will have 1 redundant equation that will not give you any additional result. So you can apply first sum of x equals 0, then sum of y equals 0. Sum of x equals 0 here will give you that AX is 0. So you are done with the first unknown. But you still have 3 unknowns: MA, AY, BY. And you can only write 2 additional equations: sum of forces along y0. And you can select any point and say sum of moments about this point 0. Now you can tell me we already used sum of moment about A, why we can't use sum of moments about B equals 0? Because this will give you a redundant result. Because in statics, you can maximum solve for 3 unknowns. You can try this. If you do these 3 equations, you will have this equation will be redundant. This means it can be proportional to this one, or it can be obtained by a proper combination of these 2 equations. So if you put the system, you will not get a solution. Okay. So these 2 equations, you have a freedom to select them. You can take sum of y equals 0 with 1 moment equation, or you can take 2 moments equations, and you can say, let me apply sum of moments about A equals 0 and sum of moments about B equals 0. Whatever you do, whatever is the combination you try to get, you will not be able to solve for the 3 unknowns. Okay? Because in statics, in 2D equilibrium, you can maximum solve for 3 unknowns. So the challenge will be then to go to another analysis to get a force equation. And now, since we defined in this course how we calculate deflection, the deflection concept will help us into calculating our force reactions. In closing, if you want the system of 4 unknowns. Why? Because if you do the analysis here, you know that at the roller, you have 0 deflection. And at the fixity, you have 0 deflection and 0 slope. Okay. And now, then how many conditions you have for deflection and slope? You have 3 conditions. At A2, x equals 0, theta equals 0. And at B, you have a third condition that at x equals L, the deflection is 0. So you have from deflection analysis 3 equations to write. However, when you want to solve for deflection, you just have to apply 2 boundary conditions, because when you integrate the moment twice, you will get that EIY equal to double integration of mx dx, so plus C1x plus C2. And therefore, to get C1, C2, you can just apply these 2 conditions. But you still have 1 condition that you didn't use. This condition that you didn't use yet will provide you with an additional equation that will close the system of unknowns and will allow you to solve for your reactions. Okay? So the idea is that introducing the concept of deflection, I introduced 2 unknowns only, C1 and C2, but I have 3 equations. So 2 equations will give me C1 and C2. And the third one will help me to find my reaction. So in total, the total number of unknowns here will be AY, AX, MA, reaction moment at A. I have also BY. And I have, in addition, C1 and C2. So in total, 6 unknowns. And now I can write 6 equations, because from statics analysis, I can write 3 from statics, and 3 from deformation analysis. So in total, 6 equations, 6 unknowns, I can solve for my system. So this is the idea of how to use the deformation concept to get reactions that cannot be statically determined. Let us do an example on this. If we go back to the problems, we were discussing this problem here. They gave us that for the beam and loading shown, determine the reaction at the roller support. I want to find the reaction at the roller support. Let me look at my figure. I have a roller support at B and a fixity at A. So as we already mentioned before, we have just to consider at A 3 unknowns, AY, AX, and a reaction moment, MA. You can assume a direction for MA, and from the analysis, you will know if it's positive or if your assumption is true or not. And you have BY. Now, to start with, okay, we can say, you can start by writing the statics equation, or you can start by getting the expression of the moment. It's up to you. You can start from wherever you want. So here, for example, what they did first is that they did a cut here at this level. And when they did the cut, because here you have much more unknowns, they kept the right part. And they said, I will do analysis on the right part. Okay, I want to find the expression of the bending moment of the right part. Of course, it will be function of By, because By is not calculated yet. So I can write the bending moment equation, function of By. So after I do the cut, I should pay attention as usual that my x is starting from the origin. So this distance is L minus x. Now I have a triangular load. So for this triangular load, I have that I need to get the equation of W function of x to be able to determine what is this distance here. Here, what is omega of x? Because I needed to perform my calculation. So I need to determine what is omega as function of x. To do this, it's very simple. I have here a beam of length L. This total length is L. And the distance from this point to the cut is x. So using Thales' theorem, I can write that x over L equals to Wx over W0. So x equals to LWx over W0. So I have a linear variation for omega. Okay. Sorry, and of course, I need to express omega x function of x. So I can write omega x equals to omega 0 over L times x. So it's omega is varying in a linear way with x. I can verify my results that at x equals 0, omega is 0. And at x equal L, if I replace L and L simplify, I get omega x equal to omega 0, which is right. Okay. So because at the end of my beam, value of omega is omega 0. So this distance here represents omega 0 x over L. And now I have a trapezoid here. When I have a trapezoid, the best approach would be to divide it into a triangle and a rectangle. So I divide it into two parts. And then I say that I can replace my distributed load by two forces. One, so let me do a bigger figure. So this distance is L minus x. For the rectangular load, I can replace it by a force at the center. So here, this is the rectangular load. And the value of it is L minus x times omega x. So it's L minus x times omega x, and omega x is omega 0 times x over L. So this will give me the rectangular force, and it's at a distance from the cut. It's at L minus x over 2. So this is for my rectangular part. Now, for my triangular part, so for my triangle here, first, the point of application is at 2/3 of the base length from this point, and it is at 1/3 of this length from the base of the triangle here. So I can say that I should move from here L minus x over 3, or if I take from the extremity point, I should move a distance of 2/3 L minus x. So this distance is 2 over 3 times L minus x. And the value of the force of the triangle is base times height over 2. So it's L minus x times this distance. This distance is the difference between omega 0 and omega 0 times x minus x. Okay, so because look, this is your triangle. The whole distance here is omega 0, while this distance is omega x. And this distance is already found. It's omega 0 times x over L. So what is the length of this side here, which represents the height of my triangle? It's the difference between these two. So this is omega 0 times 1 minus x over L. Okay, and then to find the force, this force here, you can say that the force of the triangle is equal to base, which is L minus x, times height, which is omega 0 times 1 minus x over L, you can replace 1 minus x over L by L minus x over L. Over 2. So this is the force, okay? But you need, then when you write the moment, you should multiply the force by the distance, okay? So now let us write some of moments about this point. If we consider, let's say, the counterclockwise direction as positive, so we have that the triangular load is producing a counterclockwise moment, and also the triangular load is producing a clockwise moment, and the rectangular load is producing a clockwise moment. So both are positive. And then we still have the RB, okay? So RB, depending on the convention you take. And here, for example, we said we want to take the counterclockwise as positive. وهن clockwise, and you take them as minus, okay? And in case you considered a clockwise direction as positive, you can take them as positive. So it's up to you how to take the positive convention. Depending on how you select the positive convention, then you will see if they produce positive moment or negative moment, okay? So it's a little bit now a lot of information. Let me clear and just repeat the ideas, okay? So here we have to do some of moments first about this point. to get the expression of the bending moment. Okay, so first we say we have that this bending moment is positive when it's compressing the upper part. So this is the direction of the positive moment. Okay, and we have that the distributed load, both the rectangular one and the triangular one, are producing about this point clockwise moments. So when I add moments, M and F triangle and F rectangle will be considered all positive if I take the positive clockwise direction in the clockwise direction. And if I consider the counterclockwise direction as positive, the three of them will be considered as negative. So here, I think they did a small sign error because you have minus M, and here it should be minus and minus, because all your, if you consider the counterclockwise direction as positive, then you have that the three moments created here will be negative, and the only one that is positive is the moment of RB. Okay, the moment of RB, because RB is producing a counterclockwise moment about this end. So you do plus RB, so minus M, plus RB times L minus X, minus, now I start, if you start with, let's say, the load of your triangle, okay, for your triangle, we said that the force is equal to half times omega 0. So it's half first time. Let us do this distance. So the force was L minus X times, as we already said, the difference between, so omega 0 times L minus X okay, because we said, if you remember, that this distance here, this distance is omega 0 times 1 minus, so omega 0 times 1 minus X over L. And if we do same denominator, we get that this value, the value here of this height, is omega 0 times L minus X over L. So we can replace now the force. Okay, the force is half times L minus X times omega 0 times L minus X over L. And now don't forget to multiply by the distance. So this is F. To get the moment, we should multiply about this point. We should multiply by this distance, which is 2 times L minus X over 3. So now in total, when you multiply by 2 times L minus X over 3, you'll get the following result. 2 and 2 will simplify. You have L minus X cubed. Okay, so in total, the moment of the triangular load will be L minus X cubed times omega 0 times omega 0 over 3L. Over 3L. Okay, and you can verify that this is you can verify the dimensions, the units. Okay, if you do here, this is meter cube, and this is Newton per meter square, and this is meter. So you should get in total for the moment, you should get Newton times a meter. You can verify this here because what you have is, sorry, here you have a Newton per meter for omega because it's a linear distributed load. So it's a Newton per meter. So in total you have a Newton per meter square times meter cube. So you can verify that your units are working well. Okay, so this is the expression of the moment created by the triangular load. Now we should find the expression of the moment created by a rectangular load. So now for the rectangular load, you have the following. For the rectangular load, as we said, the force is equal to omega 0 times x over L times L minus x So if you calculate the corresponding value, this is the value of the force. You still need to get the moment. You still need to multiply by the distance. The distance from the end point here, okay, to your point of application of the force is L minus x over 2. So you get that you have omega 0 times x times L minus x square over 2L. So this will give you the expression of the moment created by the rectangular force. Okay, and again you can check for your units. So here you have x times L minus x square. It's in meter cube over L, so it's meter and meter square, and you multiply by Newton per meter, so it's Newton times meter. So it's okay as unit. And now once you find the expression of the moment of the rectangular force and the expression of the moment of the triangular force, you have to add them to M and do minus RB, or here they are negative. The 3 are negative because you are considering counterclockwise as positive. And you have to add the moment of RB. So plus RB times L minus x will give you 0. This will allow you to get the expression of your bending moment. So now you can get the expression of your bending moment after doing expansion. Here it's a little bit heavy calculation, but just it's development. You should develop term by term. And once you develop your terms, you can end up with an equation for bending moment function of x. Once you have this equation, then you can perform your integral procedure. So we have, this is the expression, let's say, of the bending moment. We do first, we say that the bending moment can be replaced by EI, second derivative of y with respect to x. And then we have the expression here. This expression should be integrated with respect to x twice. If I integrate the first time, I integrate each term. So here I have RB times Lx minus x squared over 2 minus omega 0 over 6L times x4 over 4 minus 3 over 2 L squared x squared plus 2 L3x plus constant C1. This is the first integration. I do now the second integration to get the expression of EIY. So for EIY, when I do the first, when I integrate this term, I have RB times the integral of Lx is half Lx squared. The integral of half x squared is 1 over 6x cubed, and we have the minus, so minus 1 over 6x cubed. Now we have a constant, so minus omega 0 over 6L times. The integral of this term is, integral of x4 is x5 over 5, and we already have 1 over 4, so it will give you x5 over 20 minus, because the integral of x squared is x cubed over 3, so this will give you, 3 will cancel out, so this will give you minus 1 over 2L squared x cubed, and then the integral of 2L cube x will give you L cube x squared plus C1x, and of course, don't forget to add the constant C2. Now you got the equation of EIY as a function of x, and you have two constants to determine. To determine your constants, you can use the boundary conditions at the beginning of your beam at support A. So going back to the figure, at support A, we have for x equals 0, y equals 0. And for x equals 0, dy by dx equals to 0. So if I go back to my expression here, I can say that for x equals 0, y equals 0, replacing in this equation will give me that all of these terms will cancel out, and then C2 should be 0. Second step, to solve for C1, I replace into the equation of dy by dx, I replace at x equals 0, dy by dx equals 0. All of these terms will cancel out, and then I can deduce that C1 is 0. Now I got my constants C1 and C2. Next step, I still have one condition that I didn't apply for the displacement, for the deflection of the beam, which is the condition at B. At B, I have a roller, so also y at B will be 0. And I will use this condition to get now what is RB, okay? Because I expressed the deflection function of RB. So now if I go to my equation of deflection, and I say that at x equal L, the deflection is 0, I can find out that by replacing here, so I do RB times half L cube minus 1 over 6 L cube minus omega 0 over 6L, L5 over 20 minus half L5 plus L5 plus C1L. C1 is 0. Sorry, this is Y equation. I should replace. Yes, it's right. So in Y equation, C1, C2 are equal to 0. I just have to replace X by L. And then by doing so, I will get an equation with one unknown. Okay. So this will give you, after development, if you take, if you want to have RB, this is equal to, we said 0, okay? And we can simplify here L cube and L4. So we just have then, from this side, we have just L. So RB times L times 1 over 2 minus 1 over 6 minus omega 0 over 6 times this term. We can calculate the numbers. Then we can get RB function of omega 0 and L. And you can make sure, always make sure of your units to make sure that you didn't do a certain wrong simplification. Or so omega 0 times L unit is in Newton, because omega 0 is in Newton per meter and L is in meter. Since omega is force per unit length here, it's a linear distributed load. M and M will cancel out. So your dimension of units is right. And then you got the value of RB. And once you get RB, if they want all reactions, AX, AY, MA also, all you have to do now is to go back to your initial figure and say, let me apply the statics relations. I can write 3 statics relations. Sum of X equals 0, sum of Y equals 0, sum of moments equals 0 to get my unknowns at A. But here, no need to do this because they just asked for the reaction at the roller. This is why always try to do the to go straight to the solution, because they only asked for RB. The best way to deal with is to take just this part. Okay, do the analysis on this part, because in this part we have only RB. The other unknowns are not included. So no need then to get AX, AY, MA if they didn't ask you for that. So this is for the statically indeterminate, how to find statically indeterminate reactions. Here there is some errors. I will fix them for you, okay, in the PDF, some sign errors. Another problem. Determine the reaction at the roller support and draw the bending moment diagram for the beam and loading shock. So in the following figure, we have also a fixity and a roller, and we want to find the reaction at B. So this is a little bit similar to what we have seen before. Same concept. I should use the 3 equations of that I can get from the deflection. I can say that at A I have a fixity, so I have 2 conditions. I have that X is 0, at X equals 0, Y is 0, and at X equals 0, the slope dy by dx is also 0. Now for the roller at B, we have that at X equal to L, Y is equal to 0. So we'll use these 3 equations as equations to help us into getting our unknown reactions. Now to start with, we can consider, here we have 2 sections. We have one between A and C and one between C and B. Okay. We can, if we can consider first, so we have the first section for X between 0 and L over 2. And the second section will be between L over 2 and L. So now to start with, if we consider the expression of our first section, okay, here we have, for the first section, we can keep this part, okay, because we don't want to, we don't want to get the unknowns AX, AY, MA involved, okay. So we just want to find C1, if you want C1 and C2 of the equation, but we can select this part because it will only include BY and it will not include then AX, AY, and MA, okay? And why we need to do the 2 sections here? Because here, it's not like in the previous problem. In the previous problem, you only need 1 section. And this is why because you only need one section, the constant C1 and C2, you have only two constants C1 and C2 to find. Because here, if you go back to the figures, the type of loading is not changing. You have one distributed load from the beginning to the end of your beam. So no need if you want to do more than one section. And because you have just one section, you have one bending moment equation. And when you integrate to get y, you only have two constants, C1 and C2, to calculate. And these constants, C1 and C2, can be found by applying conditions at A, because the equation of y is the same for the whole beam. However, in the second example they are giving you here, we need to do two sections. We need to do one section here and another section here. Okay, and for this reason, you need to go for the equations of section 1 and the equation of section 2, and we'll see that you have four constants to find: C1, C2, C3, and C4. And of course, as we have developed last time, to solve for these four unknowns, you will use the concept of continuity at C. So you have to use the concept of continuity at C in order to relate your constants. Okay, so let us start first with the equation of the first section. If we do a section here, this distance is L minus X. And because we have the cut and we keep this part, then the bending moment to consider is like this. And then to solve for this bending moment, we do sum of moments about here. If you want, you do so here. This is let me do it for the bending moment. So this is the bending moment M. If we take the positive direction as clockwise, you have plus M. And you have plus M0. Now for the support reaction at B, RB is producing about the section here a counterclockwise moment. So it's minus RB times L minus X. Equals to 0. So you can say that the bending moment for section 1, Mx, is equal to RB times L minus X plus minus M0. So this is the equation of bending moment for section 1. And now you can do another section to get the expression of the bending moment for section 2. Section 2 is after M0, so it's here. And then for section 2, this is your X, this is your L minus X, and this is RB. So for the second section, it's simpler. You just have the bending moment at section 2. So let us say this is M2 of X. And you have, this is RB. And this distance is L minus X. So the equation will be the sum of moments about this point equal to 0. And this is, if we take the clockwise direction as positive, so it's plus M minus RB times L minus X equals to 0. So for section 2, M2 of x is just RB times L minus x. Now, once you find the expression of the bending moment in the two sections, you can integrate for each expression, you can integrate it twice to get the deflection equation. Okay. Here in this problem, I started first by using the statics on the whole beam to relate the reactions. So if you apply, they applied first sum of y equal to 0 to get a relation between RAY and BY. So RA plus RB equals to 0. This means that RA is minus RB. And also they did sum of moments about A equals to 0 in order to get an expression of the resistant moment at A, function of RB and M0. So you could have done this if you want, but it's easier to not get into, since they only need you to find the reaction at the roller. It's fine if you don't get these unknowns, AX, AY, and MA. If you want to take when you get section 1, if you want to take this part, then you should express these reactions function of RB. So you have always several methods to work with. Okay. So anyway, here they started first by because they asked you to draw the bending moment diagram for the beam. Then you need these reactions. But if you just want to find the roller support reaction, it's fine if you don't get them. Okay. So here, to draw the bending moment diagram, you should determine the reaction moment. Okay. The reaction moment at A, and to do this, so as we said, we apply first statics equation. Sum of x equals 0 means that AX is 0. So we are done with it, with AX. Then we move to a sum of y will give us RA minus RB, because we only have two reactions in y, RA and RB, and we don't have any load in y. So as you can see here, you only have couples. So RA is minus RB. And now if you write sum of moments about A equals to 0, you get taking the counterclockwise direction as positive, you get minus MA minus M0 plus RB times this distance L equals to 0. So you will be able to express your moment at A function of RB. And to be able to draw your moment diagram, you need first to determine what is RB. And to determine what is RB, we should do the approach we did together. We should find the equation of M for both sections. As I told you here, because you already found, if you want, your bending moment at A function of RB and also your reaction at A function of RB, when you do section 1, you can take this part because already the forces here are and moment are expressed function of RB. Or you can do what we did together. Both will give you exactly the same result, because as you can see here, they did the other approach. They did a cut. They considered this part, but they end up with the same result, that the bending moment is minus M0 plus RB times L minus X. This is the same result we got together. Okay. So we are done with this part. Then, as we said, we should integrate it twice. So we integrate the first time, we get the integral of minus M0 is minus M0x. The integral of RB times L minus X is RB times Lx minus x squared over 2. We don't forget to add C1. Integrate another time to get y. So EIY is minus half M0x squared plus RB times half Lx squared minus x cubed over 6 plus C1x and plus C2. Now, once we are done with this step, then we can say that this is the equation of deflection for first section. Now, this is not the same equation for the second section because the equation of bending moment is different. So for the second section, I also need to get an expression for y function of x. This is why I should find M2x as we did together. It's RB times L minus x. and we integrate it twice. When we do the first integral, we get a constant C3. When we do a second integral, we get RB times half Lx squared minus 1 over 6x cubed plus C3x plus C4. Now, as we said, we have 4 constants to determine. And we should apply the continuity principle to be able to close the system of unknowns. So as we mentioned already, we have first a fixity at A. So at A, we can apply the following 2 conditions. At A, the slope of deflection is 0. If we apply this, we get constant C1 equal to 0. At A, the deflection is 0. Applying this relation, we get C2 is 0. Now, at X equal L over 2, which is the point if you want, the extreme point between the 2 sections, separating section 1 from section 2. As we mentioned before, at any point that is between 2 sections, we can always apply 2 continuity equation. One continuity equation for the formation, deflection value, and one continuity equation for the slope of a deflection that will be the same. So here at X equal L over 2, which is the point separating the 2 sections, I can use first continuity of slope. So I go back to the slope equation, so to dy by dx of section 1. dy by dx at section 1 is calculated. I just have to replace x by L over 2. So I get minus m0 times L over 2 plus RB times half L square minus 1 over 6 L square equals to, for the second equation of dy by dx, I replace x also by L over 2. I get RB times half L square minus 1 over 6 L square plus C3. I can see that there are 2 terms that are equal in the 2 in my equation, so I can cancel them. And then I can get what is C3 function of M0. So this, if you want, the continuity of a slope will give me what is constant C3. And now, once I know C3, I apply continuity of deflection to get the expression of C4. So if I apply continuity of deflection, I go again to y equation of section 1 equal to y equation of section 2. In these equations, I replace x by L over 2, and then I simplify equal terms to get a relation between C4 and C3. Once I get this relation, all I have to do is to replace C3 by its value in the equation, and then I can get C4 function of M0 and L, which are known. So I found C1, C2, C3, and C4 by using 2 conditions on deflection and slope at A, and 2 continuity relations at the point separating the 2 sections. But I should keep in mind that there is one relation that I didn't use yet, which is the following, that y at B, the deflection at B is 0. And of course, for the deflection at B, I should take the equation I got from second section, because B is only in the second section, it's not in the first one. So pay attention. I will say y2, so y of section 2 at x equal L should be equal to 0. This relation will allow me to get what is the value of RB. And then I can solve for the reaction at the roller support. So as you can see here, after finding my constants, C3 and C4, I now replace into the equation of y of section 2. And for y at section 2, at point Bx is equal to L. So replacing x by L in y2 equal to 0, I get the expression of RB, function of M0 and L. And once I get the value of RB, I am done, if you want, because now I already expressed before the reaction. We said that RA is minus RB and MA is function of RB. So if we replace into our equations that we found before, we can find what is the value of reaction at A, what is the reaction moment at the fixity, And then we can draw the bending moment diagram, because once we know the value of RB, we already expressed our sections. So bending moment mx in section 1 is expressed function of RB, and bending moment m2 in section 2 is also expressed function of RB. So once you have RB, you can replace at points of interest to get the values of bending moment required for your moment diagram. Because if you go back to the figure, to draw the bending moment diagram, what do I need here? First, I need to know what is the value of MA. To get the value of MA, I already used the result here of MA function of RB. I replace RB by its value, which is function of M0. And then I get MA function of M0, because look, RB was found to be, so RB is 9/8. So RB is 9/8 times M0/L. So going back to your equation here, if you replace RB by 9/8 M0/L, you will get 9/8 M0/L times L, so L will cancel out, minus M0. So this will give you 9 minus 8/8, so 1/8 M0. So, and MA is in clockwise direction. So you start with a positive jump at A. So you start your moment diagram by plus 1/8 M0. So this is why we start here by M0/8. Now, what do we have? We have, if you want, for V in section 1, V in section 1 is equal to minus R. Yani if you consider the equation like this, okay, to get the value of V, you can find the expression of V function of RA. So you will know that your moment will be decreasing in this section. Because if you want to find the expression of V, so this is our, or if you want, no need here to do the area method, because you already found the equation of M, okay? So if you didn't find the equation of M, of course, you can use the area method, and you will see that because V is negative in this region, then you have that the bending moment will be decreasing in a linear way, okay? Because RA is negative, RA is minus RB, okay? So since RA is negative, then your shear is negative in this zone because you only have the reaction at A, and RA is downward. So you have a negative shear in this part. This will explain why M is varying linearly and it's decreasing. And also you can see this from the equation, from the bending moment equation in section 1 that we found together. So we found together, if you remember, that in section 1, the equation of M is given by this. So it's minus M0 plus RB times L minus X. And since we found now the expression of RB, so all we have to do is to plug in, or instead of RB, we put the expression, which is 9/8 times M0/L. So let us do it. So it's minus M0 plus 9/8 M0/L. So this is RB times L minus X. Okay. So for X equals 0, you get this this term will give you L. So you have minus m0 plus 9 over 8 m0, which is m0 over 8. And for x equal to L over 2, to find the value of bending moment just here, I replace x by L over 2 in this equation. So here I put instead of x L over 2. So I get minus m0 plus 9 over 8 m0 over L times L over 2. So here L and L will cancel out. So you have minus m0 and you have plus so as we said, it's plus 9 over 16 m0. So you have minus 16 plus 9 is minus 7. So here you have minus 7 over 16 m0. And now you can expect that at this point I will have a sudden jump in moment, and I can verify this to make sure that my equations are right. I can verify this from the equation, and I can expect that because I have a clockwise moment here, I should have a jump equal to plus m0 upward. So because I was at a value of minus 7 over 16 m0, if I plug in x equal L over 2 in the equation of m2, I should get plus 9 over 16 m0. And you can verify this easily by replacing into the equation m2 function of x. And also, you can expect that at the end here, I should end up with the bending moment of 0, because at this point, I don't have a couple. So replacing by x equal L in m2 of x, you can verify that I will end up by 0. So in this way, I will be able to draw my moment diagram. And then I am done. I found the reaction at the support B, and I was able to draw my moment diagram. Another problem, determine the reaction at A and draw the bending moment diagram for the beam and loading shock. So again, we are, if you want, repeating same ideas. So here we have first a statically indeterminate beam, because I have 3 unknowns at A. I have AX, I have AY, and I have a bending moment. So you can assume a direction for MA. And same for B. I have also a fixity. So, but you can say, if you want here, you can say that due to symmetrical effect, I can say that BX should be opposing AX. Okay, so AX will be minus BX, and I can see this from sum of X equals 0. Also, AY and BY will be equal. So you can just say from symmetry of the figure, AX equal minus BX, AY equals minus BY, and MA equals to minus MB. Or if you took already the convention that they are opposite on the figure, then you can say that MA is equal to MB in magnitude, and they are just opposite in sense, as you can see in the figure. So from symmetry, you reduce your unknowns from 6 to 3. And now you want to solve for your reaction at A. Okay, so to solve for your reaction at A, you should use the equations of deflection, because from statics already you used the effect of symmetry. Already from statics, you were able to find, when you write these 3 equations, sum of X equals 0, sum of Y equals 0, sum of moment equals 0, you deduce the symmetry results that are B equal RA and B equal MA, AX equals BX, and they are opposite. And just then we have still 3 unknowns. 3 unknowns to find: AX, AY, and MA. So we need 3 additional relations to solve for these unknowns. So we will use here, we will use the concept of deflection analysis to get our unknowns. So first, we have a fixity at A and we have a fixity at B. This is why we can say that at x equals 0, y equals 0. At x equals 0, derivative of y with respect to x equals 0. And also for B, we have 0 deflection, 0 slope. Okay. So this will give us 4 equations. But how many unknowns do we have? We know that for deflection, when we write the equation of deflection, we get C1, C2. Okay, we get 2 unknowns, C1 and C2. And already we have 3 equations. We have 3 unknowns, AX, AY, and A. So in total, we have 5 unknowns. So we have 5 unknowns, but 4 equations, 4 additional equations here. So what can we use here? The symmetry concept will also apply will give us a condition on deflection. Because look, because of symmetry, when you draw the deflection curve, the deflection curve will also be symmetrical with respect to this axis. And because of this symmetry, you can say that you can expect here a maximum deflection at the middle, and therefore the slope of deflection is 0 at L over 2. So this will give you an additional 5th equation that at x equal L over 2, dy by dx is 0. And then I have 5 equations and 5 unknowns, so I can solve for all of my unknowns. Okay, so this is the strategy in this problem. So as we said, the first step is to use the symmetry concept to relate reactions at A and B. Once we do this, we say that for the entire beam, let me find an expression for the bending moment. Here, since I have a one distributed load, so I can consider that I need only one section. So if I do the section, and I say this is my distance x, and this is a reaction RA, I can write that sum of moments about this point equal to 0. So I have plus m. Now if I take the counterclockwise as positive, I have plus m. I have, for the distributed load, I can replace it by a force at the center equal to x times omega. And I have x times omega, and the distance separating the force to the point is x over 2. So for this force, it's producing a counterclockwise moment. So it's plus omega times x squared over 2. And I have also the moment of RA. RA is upward, so it's producing a clockwise moment. So it's minus RA times x. And finally, I have also the effect of the reaction moment at A, which is in the negative direction. So minus MA equals to 0. Now, if you take all terms to the other side, you get that M is minus omega x squared over 2 plus RAX and plus MA. So this is the result I found here. Now, I do double integration to get the expression of y. So I can say first that the bending moment is equal to EI times second derivative of y with respect to x. When I integrate the first time, I get MAX plus 1 over 4 omega Lx squared minus 1 over 6 omega x cubed plus C1. And here, I can start to apply the boundary conditions for the slope of deflection. We know that at A, the slope is 0. So at x equals 0, dy by dx is 0. Because we have a fixity at A, this will give us C1. Now, using the symmetry condition, we have that at x equal L over 2, dy by dx is 0. So this will allow us to solve for MA. Okay, because now if C1 is 0 from the first boundary condition, let me use now the symmetrical condition that at x equal L over 2 dy by dx is 0. Then I get an equation where the only unknown is MA. This will allow me to solve for the reaction moment at A. Once I am done here, then if you want, knowing the value of MA, I know the value of the equation of the bending moment. So bending moment will be equal to minus 1 over 12 omega L square plus half omega Lx minus half omega x square. So I can now draw the diagram of moments. And here in this problem, what I asked for is just to determine the reaction at A and to draw the bending moment diagram. So I already found the moment at A, okay? And I have that by symmetry, we said that RB equal RA and equal to half 1 over 2 omega L. So from symmetry effect, you can also find the value of RA, RB from statics, because you have that the whole load here is divided, is supported by A and B. And since A and B are equal, if you use the static equation that sum of y equals 0, you get that RB plus RA, but because they are equal, so you can replace RB plus RA by 2RA, and 2RA should balance the distributed load, so it's equal to omega times L. Okay, so this will allow you to find what is the value of RA. So RA is omega L over 2. Okay, so even we didn't need to apply conditions at B. And of course, to find RA or RB, you can also use the deflection equation. You'll exactly find the same result. Okay, but here the symmetry will help you a lot into reducing the computation, because from symmetry, RA equal RB, and they will support both together omega times L. So each one will be omega L over 2. So we were able to get RB and RA just from statics, while for the bending moment, we need to perform the deflection analysis. And this is what we did. From deflection analysis, using the concept of symmetry, we were able to find the value of the moment at A function of our omega. And then once we found MA expression, we are done, because already we determined RB, RA. And here, for X reactions, if you want, for AX and BX, you know that they are opposite, okay? And you can tell me that we didn't find them. So how we can make sure they are 0? In this problem, you don't have a load in X. So this can justify, because you don't have a load in X at all. Then, and you don't have, if you want, like we have seen before, if you remember in statics, if you have thermal effect, you can have expansion of your beam. But here you don't have any data about this. So we can consider that since no X load is applied and there is no source for, let's say, stretching of the beam, then we can say that both AX and AY reactions are, AX and BX reactions are 0. Okay, so here we just had to go into deflection analysis to get MB equal MA. And if you use the deflection analysis instead of statics to get RB and RA, you will also find that RB will be equal to half omega L. So both statics analysis or deflection analysis will give you the same result for the expression of RB and RA. Because you can verify here that from the equation you got, if you apply conditions at B, when you apply conditions at B, you will verify that at X equal Ly equals 0 and at X equal L dy by dx is 0. And this will be, of course, the case because you already used the symmetry concept. And because of the symmetry concept, the y, the deflection equation will be symmetrical. And the value of, if you want, the reaction is the value at B. If you want to illustrate it accurately, we have a slope 0 here. So the deflection slope 0, it's like this, and then it's like this. So you have a symmetrical deflection curve, and conditions at A are similar to conditions at B. This is why it was only needed to use relations at A because of symmetry, and to use the maximum deflection at the middle, which also gave us an additional equation that dy by dx is 0 at L over 2 to close our system of unknowns. Okay. Now, another problem for the cantilever beam shown determines the slope and deflection at the free end. So here we have a beam supported by a fixity at A, and we want to determine what is the slope and deflection at point C. Okay. So to do this, we have several approaches. We can use, if you want, the conventional methods that we did already, which is to do several sections. And we take section 1, we take section 2, we find the bending moment equation in section 1, we find the bending moment equation in section 2, and as usual, we apply continuity of slope deformation, continuity of deflection, and continuity of slope of deflection at B to add 2 additional equations, and therefore we'll be able to solve for C1, C2, C3, and C4. And then once we get the equation of deflection in part 1 and in part 2, since C is a point of part 2, we determine the deflection at C by replacing x equal L in the equation y2 of x. So this will give us y at C. This is a first method that we have already developed before. Now, this problem in particular is given for you to tell you that we have another method, and the other method is called superposition method. And this is the method that we will introduce in the last section of this chapter. So now we'll go back to the course material, we'll introduce the concept of superposition, and then we'll solve this problem.